All right, so we'll go ahead and get started now. I'd like to welcome everyone to the webinar. My name is Kyle Daldana, and I'm joined by Stephen Munsey, and we are applications engineers for Zygo. Steve will be on the line to field any questions that you have. If you do have questions along the way, you can submit those through the GoToWebinar interface, and he will do his best to answer all of your questions via text through that. We also may field one of your questions throughout the course of the webinar during a brief Q&A session. And if you don't hear back from us via either of those, then we will follow up with you after the webinar. Okay. So today we will be talking about defect analysis using our MX metrology software. And to give a little outline, we'll start with a Zygo technology overview, where I'll talk a little bit about the systems we use and the technology behind them. Next, we'll talk about defining a defect and just understanding what we mean when we talk about a defect and how we might characterize those. I'll pause for a short Q&A, and then we'll jump right into different methods for analyzing defects and techniques that we can use with MX. And then we'll wrap it up with some hands-on with MX. So I'll show you an example using the software. And then we'll finish with another Q&A if there are any remaining questions. So today, when we discuss data and we talk about defects, we're talking about data that was collected using an optical surface profiler. This is a non-contact metrology instrument that utilizes white light coherence scanning interferometry, or CSI. And these tools have applications in a really wide range of industries, from research and engineering settings to development in a lab, or even process control on a manufacturing floor. So the basic technique behind the optical profilers is CSI, or coherent scanning interferometry. As I said, it's a non-contact technique that uses white light to measure height on our surface. So if you look at the diagram in the upper right, you'll see we have a light source here, a white light source. This light is sent down through our interference objective and then down to our measurement sample. And at the bottom face of the objective, we have a beam splitter. Part of the light is sent down to the sample and reflected off of our surface. And the other part of the light reflects off of the beam splitter and to our reference mirror inside the objective. These two light paths are recombined and imaged by our camera, and this generates an interference fringe pattern that you see in the bottom right. Because we're using white light and it is incoherent, we get a nice fringe contrast envelope, and this is what we'll use to scan our surface in Z to acquire height data. So as I said, we'll scan our objective in Z across our measurement surface. And then for each peak in contrast for that fringe envelope, the peak will correspond to a height value. And so for any positional difference that we see between peaks will correspond to a difference in height on our surface. So you can see as our objective scans, we hit point A, and it corresponds to the peak contrast for signal A, and the same with point B, and then we get our height difference between these two. Now, the interesting thing, I think, about this is that we use a 2D camera array to image this. So for any given scan, we have over 1 million signals to process. Now, the way that we actually use these signals and this scan is in generating a 3D topography map of our surface. And you can see I've included a few examples here on the right. And this is really just to highlight the wide range of surfaces that we can actually measure. Up here, we see well, it's not obvious, but this is a very polished optical flat. We have things like the diamond turned micro lens, or any machined part for that matter. Even down to something that's very porous and fibrous, like this banknote. So the application range is very broad, and we're really talking about any surface that we can capture any reflection from, not necessarily in the conventional sense. You don't necessarily think of a banknote as reflective, but it is in fact, and enough so that we can acquire height data on that surface. So we'll get into defining a defect now. So in a very general sense, a defect is any any abnormality or feature or deviation in a product that affects its ability to perform properly. There can be many causes of this. I listed a few here, which would include something in the manufacturing process to cause a defect. It could be the handling of the product after manufacturing, or even in assembly during that procedure. Or it could just be a flaw in the actual design of the product to begin with. So I have a few examples just to sort of show you what we're talking about. This is an example of a MEMS microphone. And here we can see visible and detectable film delamination on this sample. It could be caused by an issue with the manufacturing of this device, or a flaw in the actual design of that film in the first place. This is an example of a diamond turned micro lens. You can see very obvious scratches on this surface, as well as lots of pitting within the surface in the material. Something like this, though these are from some alternative metrologies, in this particular case, we could attribute something like this to product handling, or even testing of the sample that results in this. And then for the different pits that we see and these little defects in the material, there can be some particular abnormality with the material that was used that could cause something like this. And then finally, we have an example of a precision machined surface. In this case, we can clearly see the presence of different defects on this surface. Something like this technique, where maybe you use a stereo microscope and you place your part under that microscope, and you're looking for the presence of a defect, and maybe its approximate position. And this is about as much as you can acquire with that technique. When we use MX, we get that qualitative aspect, but in addition to that, we get a quantitative analysis, which allows us to really accurately define each defect and use a wide range of parameters to define those. So with our defect analysis, it's often very sample and application dependent. So we have a lot of options, and there's really a wide range of things you can do, which is why it's so application dependent. But ultimately, it allows us to collect data and then isolate the defects from our surface and determine, the exact dimensions of those, as I said previously. Now I have listed a few common measurements here. Some of them will capture something like the size of a defect aerially. So I have minimum enclosing rectangle. I also have the moments calculation, which we'll get into a little later. We have the more obvious ones like location or shape. And then we also have things like height and depth of different defects. From that, you can also calculate things like volume. So at this point, I will pause to check with Steve and see if we have any questions.
Thanks, Kyle. So it looks like we have one question at the moment, and that question is, what is the smallest defect that I can measure?
That is a good question. So, excuse me. In terms of the size of the defect, it's going to be very much dependent on the particular objective that you use in your optical profiler configuration. So we have a wide range of objectives from something very low magnification, like a 2x, even a 1.4x, up to a very high magnification, like a 50x. And at that point, your field of view in that 50x is about 200 microns square. So really the smallest defect is well within the micron range. And it's important to note that these different magnifications do not affect our ability to resolve vertically, meaning that your precision and your accuracy will not change based on the optical magnification. That is a constant for our systems, so they maintain that accuracy.
Awesome, thanks. It looks like we have one other question that just came in. How are different reflectivities handled by the system?
Yeah, so different, in a sense, you don't necessarily need to do anything to accommodate different reflectivities. We automatically adjust for the amount of light passing through the system, and in this case, or in any case, we always have the optimum contrast. Now, once you get down to particularly low reflectivities, you may start to see issues with fringe contrast, but these are very low percentages, like sub 1% reflectivity. So at this point, there's almost no signal to measure in the first place. But otherwise, it doesn't matter what the reflectivity is necessarily. There's no need to match reflectivities like you might need to do for something like a laser interferometer. We're very capable of a wide range there.
Awesome, thank you. It looks like the only questions you have at the moment, so I'll let you get back to the presentation.
All right. So now I'll jump into different methods of defect analysis and techniques using MX. And what we'll want to start with is a very basic overview of data processing. Data processing is going to be something that's included in almost all of your data analysis in some way. In this case here, we have a curved surface, and after applying processing to this, you can see we've removed all of this, this gross form, And it really highlights for us the turning marks on this surface, as well as this very clear defect in the form of some ridge. So we can remove things like overall form for something that's curved, maybe it's spherical or cylindrical. We can also remove things like spikes if there's any contamination that we're not interested in calculating any results on. Particular surface slopes, and also particular spatial frequencies. We have the ability to filter all of those out to show us only what we want to see. And today, when we talk about our defect analysis, we'll be using regions segmentation, which is a tool within MX. And regions allows us to segment our data and isolate defects to provide us with that very detailed analysis of each defect independently. And many of the results that are available in MX standard can be found in regions, and we can apply those to all of our defects. So now I will jump into a little hands-on with the software, just to give you a look at what we're talking about. Okay. So here we see we have this machined surface that we've measured, and it's overall relatively flat and fairly rough. But we do see we have all of these pits in the surface that all lie much lower than the overall mean of the surface here. So what we'll want to do is isolate each of these pits to perform some additional analysis on these. So in the navigator, I will switch over to regions. And this is the interface that we'll work with for that analysis. Now you see three different maps here. This is the input map that we'll use for the segmentation. In the middle, you have the currently selected region. And then on the right, we have our reference map. So this will allow us to view our regions and our data as we work. We also have the controller over on the left, and the general workflow here will be top down. So we won't necessarily hit all of these tools, but we will use most of them to apply specific settings and perform calculations on our defects. So the first thing we'll want to do is select the segmentation mode. Now there are a lot of different types here. In this particular case, I will choose Z relative, and I will show you why. When we perform these techniques, we're calculating based on the height information on the surface, and that's what we'll use for our segmentation. So in this case, we're working off of a histogram of height points in the map. And then what we'll want to do for our Z relative technique is define a height range to segment our data. So I'll expand this slightly. Okay, so I'll go down to my surface selection here, and we can scroll over, and there's a few things that we'll work with. The first one to note is the Z datum. Now this is going to be the datum that we use to apply our offsets. So our offsets will be relative to this. There's different options for this. In this case, we'll just choose the mean of the map. And then, because of the majority of our data lies within plus or minus 2 microns, I'm going to choose a threshold for our region detection. I'll start at about -3 microns from the mean. and then we'll capture everything from this point down. So in my high offset, I'll select -3. And then in my low offset, I'll choose something large just to make sure we capture everything, like -15. And so now you can see we immediately have a change here. All of our pits have been pulled out. And at this point, we've successfully detected the defects on our surface. Now, we've only gone as far as to do the qualitative sort of analysis that we would have done using different instruments. So in this case, we'll actually want to break down each of these regions to perform additional analysis. So I'll continue scrolling over in the selection, in the surface selection. And there's a checkbox called subsegment. We want to enable that. And now this is where it becomes really powerful, because we can select and isolate each region or defect independently. And you can see their location as I click through the list. So what we'll want to do is apply a few results to these regions so that we can populate our table with these results. So I'll right click and select results. And then we'll want to go to test because we want to calculate results on our test regions. So I'll go to the surface parameters and we'll start with height. So I think in this case, I want to know the lowest point in each defect so that we can determine just how deep it goes. So I'll select the valley. We'll also want to look at spatial parameters because maybe we're interested in the size. So I'll go to the moments selection and I'll select the major and minor dimension, and I'll show you what this means in a moment if you're not sure. We'll also want the position of the defect in the field of view. So I'll select center X and Y position and then choose OK. So now you can see our table has been populated with each of these results, and we can use these to determine different aspects of each defect. Now, I'll get back to the moments. So if I go to the moment options and show the rectangle, this is the dimensions that we had selected earlier. So what we're doing is actually fitting a rectangle to each region independently. And then we're determining the major and minor dimension of that rectangle. So this is giving us a very accurate representation of the size of that defect. And you can see our dimensions here. In this case, they are in microns, but you can change it to whatever units you wish. We also have the center point of each defect, and that's within the field of view. Here we also see the valley. So this will be calculated from our reference surface. In this particular case, the lowest point is at -6.8 or 6.9 microns below the mean. And this is how we would build up an application to perform a defect analysis. So there are a couple other examples that I want to touch on, but we will not cover those in the software today. So we'll jump back to the presentation. So the analysis that we just performed was using height data or height information from our surface, and that's how we were able to segment. This is an example where that technique won't necessarily work. So here we see a turned lens mold, and down at the bottom here, we can visually identify the presence of some defects, whether it's contamination or damage or whatever. but we see them here. Now, in this case, if we attempt to use height like we had previously, we would find that these particular defects fall well within the height range across our surface. So what we want to do is use a different technique to segment these out. In this case, intensity information is actually a very good technique for identifying those. And you can see in this intensity map here, we can very clearly see the darker regions where we have the presence of a defect, whereas the rest of the map is relatively light gray. So when we apply this intensity segmentation, you can see on the right, we very easily pull out each of these defects. And then in the same way, we'll apply our analysis techniques in regions to each of these to calculate whatever results we might be interested in. Now, one thing to note, we only segmented using the intensity information. When we actually calculate results, that is based on the height information. So you still get all of the same types of parameters. This is another interesting case that I want to touch on. Here we have, well, it's not necessarily obvious from this, but this is the measurement of a cylindrical lens surface after processing has been applied. So the map appears relatively flat. This is the way that we would want to process the data before we perform any segmentation techniques. However, in the same way, all of these scratches that we see, which are the defects that we're interested in analyzing, these also fall within the height range on our map. So height is kind of out the window. We don't want to use that technique. In the same way, though I don't have an image of this, the variation in intensity on this surface is such that we can't cleanly pull out each of these scratches using intensity information. So what we'll want to do is actually filter this map based on the slope information, which is derived from the height information. And then using the slope information, you can see on the right, it's trivial to pull out each defect again independently, and this is strictly based on the local slope of that defect. So those are a couple additional methods that I want to cover just to give you an idea of the sort of range when it comes to defect analysis. So just to wrap up, we looked at some data using optical surface profilers and our MX software, and we calculated different parameters and identified defects using regions. And we used 3 different techniques, being height, intensity, and slope techniques, to segment our defects and perform analysis on those. And I would say the important takeaway here is that, at least for us, for defect analysis, there are many options, and there's often more than one way to perform your analysis. So it's really best to take a look at your options and at your application and choose the technique that works best for you. So we will work with you to develop this and make your process as efficient as possible. So before we finish, I will turn to Steve to see if we have any additional questions.
Hi, Kyle. Looks like we have one additional question here. Can you have pass-fail criteria for defect analysis?
You can. So this is something that is not specific to defect analysis or regions, but can be applied to this. We have a tolerancing tool, and this allows you to set different thresholds for any given parameter that you might be interested in. And then we can apply thresholds to the result to define pass and fail criteria. At that point, when you take a measurement and regions automatically calculates the results for each of your defects in this case, it will automatically flag which defects fall outside of your tolerance. And in that case, you can very easily generate your pass-fail.
All right, thanks, Kyle. That looks like all the questions for now, so I'll let you conclude the presentation.
Okay, very good. Well, thank you all for joining us, and thanks to Steve. If you have any additional questions that maybe you didn't think of just now, please feel free to contact us at zygo.applications@amatech.com. Thanks again.